the last class, we discussed about that certain sequential data structure, and also we have told what is algorithms and data structures. Now today I like to consider the different paradigms on sequential or paradigms we use for sequential algorithms. I assume that you have the base knowledge, basic knowledge on these paradigms. However, for completeness sake, I will be covering some of these paradigms. And I will be little fast because this is you can consider it as a warm-up class so that you don't face any problem in understanding the parallel algorithms while we'll be discussing the similar type of problems. Now, the different paradigms we use for sequential algorithms are: one, divide and conquer. This is one well-known paradigms, we use it. The next one is the greedy method. Third one is dynamic programming. Fourth one is backtracking. Fifth one is branch and bound. Then you have linear programming, integer programming, and so on. We will try to discuss in detail at least these three paradigms, right? And if we can also discuss about this backtracking and branch and bound paradigms in time permits. Now let us consider the first paradigm, which is divide and conquer. What happens here? Actually, suppose you have a problem P, and that you want to solve this problem P. What we do in divide and conquer, you divide this P, problem P, into several sub-problems, P1, P2, P3, Pk. Okay, there are k sub-problems. We can divide this P problem into several sub-problems, and these sub-problems are having the similar properties as we have in the case of P. So now I solve this problem P1, problem P2, problem P3, and problem Pk, and then I combine the results to get the solution of P. Is it okay? That what we do, that we have the k sub-problems, this sub-problem, each sub-problem is smaller in nature with reference to P. Now we try to solve this P1, P2, Pk, and if I can solve this, then you combine this result to get the solution of P. Now it may so happen that P1, P2, Pk, they are also large in size. The problem is not that simple problem. Then you divide these sub-problems into further sub-problems where we can have P1, P11, P12, P13, and P1, suppose N1. Similarly is the case with P2 and so on. Now you solve these problems P11, P12, P13, and P1, and I combine this to get the solution of P1 and so on. Okay. Now Say for example, we want to find out the sum of n numbers. Now by observation you can tell that finding the sum of n number is a sequential process. Now look at the problem that I have x1, x2, xn. These n elements I have. These are the n elements x1, x2, xn, and I want to find out the sum of n numbers, these n numbers. So one way I can think that I divide this into two parts, right? Say I want to find out the sum of n numbers. Now that instead of finding the sum of n numbers, what I do here, now I find sum of 1 to n by 2, and this side I find the sum of remaining n by 2 elements. Now I got recursively the sum of this, and then I combine these two to get the sum of n numbers. Okay? So if I have to write this in the form of algorithms, I can write sum A. Say I want to find out the sum of L to U. If L equals to U, then return A L, else if L equals to U minus 1, then return AL plus AU, else return sum A L return else M is equals to L plus U by 2, and then return sum A L M plus sum A M plus 1 okay. So basically you are computing this L plus U, and then you return this sum and then plus this one. So if I have to compute the time complexity for that, then I have Pn is equals to 0 if n is equals to 1, 1 if n equals to 2, otherwise 2 Tn by 2 plus 1 otherwise. So you have to solve this, because this one is coming that one addition, and this is size is half size, so 2Tn by 2. So Tn becomes 2Tn by 2 plus 1, which I can write 2 times 2Tn by 4 plus 1 plus 1. So it gives you basically 2 square Tn by 4 plus 2 plus 1. Is it correct? The next time I get 2 square Tn by 8, 2 sequence plus 1 plus 2 plus 1. So I get 2q Pn by A plus 2 square plus 2 plus 1. So if n is equal to 2 to the power k, I get here 2 to the power k minus 1 P2 plus 2 to the power k minus 2. Now this is T2 is 1, so you get 2 to the power k minus 1. So you get 2 to the power k minus 1 plus 2 to the power k minus 2. So this gives you 2 to the power k minus 1, 2 minus 1, which is nothing but n minus 1. Okay, because 2 to the power k is n, so you get n minus 1. And which is in reality is also true, that to find the sum of n numbers, you need n minus 1 addition. Okay, so this is the first simple problem. Now you know that binary search. Let us think about the binary search. What happens? In the case of binary search, we assume the elements are either in increasing order or decreasing order. So suppose you have n element, A1, A2, An, A1, A2, An, and n argument k you have. You are interested to find whether the element k exists in this sequence of n elements or not. Now it is assumed the elements are in increasing order. Now in the case of binary search, what we do? We divide these n elements into, we compare the k with the middle elements. It has the property that if it is in increasing order, then this element is less than equals to this is equals to, and so on. So we will be comparing the middle element with the k. Now if I find that k is, less than am, where m is the middle element of the sequence, then if k exists at all, then it will be lying here. So in that case, my searching zone will be reduced to this part, and we can easily discard all the elements of my right from my searching area. Now the searching zone is reduced to this, and again I take the middle element and I compare whether k is less than, equal to, or greater than. If it is equal to m or the middle element, we tell that element exists and you got the value m. Now if we find that k is greater than this side, then k lies in this zone. So my searching zone will be reduced to this, and so on, till we process this one, till I find that there exists only one element, and you have compared and you have found either exists equal to or not equal to. Okay. Now in that case, if I have to estimate the time complexity for that, then it becomes Tn is, you will be comparing one, and the size will be reduced to half if n is greater than 1. And if n equals to 1, then only one comparison is required. Now solution of this becomes order log n. Now if I have to do, or I have to write the generic algorithms for divide and conquer, and with the understanding that we will be dividing the problem into the two sub-problems. So I write D and C, the problem P, and size is say small p and q. So this is the problem from the size of p and q. Now if problem pq is small, then solve. Else m is equals to say p plus q divided by 2, and then you call divide and conquer pm x equals to y equals to divide and conquer p m plus 1 to q, and then combine the result x with y. So this is a generic algorithm for divide and conquer. If I have to see the time complexity, Tn is equals to say Fn if n is small, else this 2 Tn by 2 plus some another function Gn otherwise. Right? So this Gn is for the time you need to combine these two results. This is an example of divide and conquer paradigms. Suppose you have x1, x2, xn are the n elements and they are not in sorted order. You want to arrange them in ascending order or descending order. Let us assume without any loss of generality, we want to arrange them in ascending order. Now, the mass sort is a technique to arrange these n elements in either in ascending order or descending order. Now, see, algorithm becomes very simple. See, if I write mod sort and you have x L dot dot u, then you can write m is equals to L plus u divided by 2. Then you write mod sort x L m mod sort x m plus 1 u. Then you have mod x L m plus 1 u. What it means that basically you have n elements, and you are dividing into the two parts. You are recursively, you are doing the mod sort of this, recursively you are doing the mod sort of this, and then this is in increasing order, this is also increasing order. You are then combining these two results to get the result is in increasing order. Okay? So m is the middle of this. You are dividing these n elements into the two equal parts. You are making the mod sort algorithm recursively. You are calling this part, mod sort algorithm calling this side. Then you are merging these two to get the results. We will be discussing how to merge this one. Okay? If it is the case, then my time complexity becomes Tn is equals to 2 times Tn by 2 plus the time you need to merge. Agreed? Now let us think about how to merge. You have A1, A2, A3, AX, and you have B1, B2, B3, By. Suppose you want to merge these two sequence with the understanding that this is satisfying this criteria, this is satisfying this criteria, and you want to merge these two sorted sequence. So what I do, I compared A1 with A2, B1. If you find that A1 is smaller than B1, then A1 is the smallest element, which is, I write C1. Now once you have selected A1, then pointer moves to this area, and I know I compared A2 with B1, and if you find still A2 is smaller than B1, then you write in the position of C1, and the pointer moves to A3. Now A3 is compared with B1, and if you find that B1 is smaller than A3, then B1 is coming and the pointer moves to this place. Okay, and proceed till one of the array already, one of the sequences already transferred to C sequence, and the remaining elements straightway bring to C to get the final merge sequence. Now here I have basically one sequence x1, x2, xl plus 1, xm, then you have xm plus 1, xm plus 2, you have xu. This is satisfying this property. That this is in increasing order, this is also increasing order. Now we have to merge it. So I can write merge x L m plus 1 u, or for me mid, and then u, I write I is equals to L, J is equals to mid, and K is the pointer for merge sequence, which is L. So I will be moving this pointer I, J, and J, and we'll see as long as the whole sequence is considered, we have to is not yet considered, we have to do these operations. So while I is less than mid, and J is less than U, we have to do the following. That means both the sequences are not exhausted. If x of I is found less than x of j, then this sequence contains the smaller elements, and that has to be moved to sequence, say, y, k is your xi, and I is increased by 1. Otherwise, xj is greater than this, so you will be writing else yk is your xj and j is increased by 1. Okay? And in both the cases, your k will be moved or increased by 1. Okay? This is the things you have to do, that if you find that xi is less than xj, then yk is updated by xi, and I is increased by 1. Otherwise, yk is updated by xj and j is increased by 1. And anyway, that you have to update the yck to get the next position of y. Now, in that process, what it may so happen that one subsequence is already entered into y sequence and some part of other sequence entered into the y sequence. The remaining part is yet to be shifted to y. Okay, so that has to be taken into account. Now, this can be done like that if you find that I is greater than equals to mid, then there exists some elements of the second subsequence to be shifted, that is for L equals to j to u, y L is your x, yk is equals to xl, and k is increased by 1. Else, for L equals to I to mid, minus 1, because of I to mid, and then yk is your xl and k is increased by 1. Okay? So basically you have merged now x sequence, x subsequence and this subsequence, and merge sequence you have put it y, but in order to get the result back to x, you have to write a small statement, that is for I equals to 1 to L to u, I equals to L to u, you have xi is equals to y. Okay? So then result will be stored back to x. Now if I have to find out the complexity of this algorithm, then you observe that it takes basically here worst case scenario. What will be the worst case scenario? Worst case scenario could be that one element, you have this subsequence and this subsequence. So you are taking one element here, then next element, then next element, next element, next element, next element, and so on. So that many comparisons, this loop will be compared every time, and which will be taking order L minus U, basically order n. U minus L, that is basically order n. And this also will take, otherwise also, data movement time also basically will find order n. So merge routine will take order n time. Merge routine will take order n time. So in that case, merge sort takes the following time or needs the following time. If Tn is the time complexity to sort, then you have Tn by 2 plus order n. This is for merging. What is the complexity now? It's coming 2 times Tn by 4. So let me write that Tn is On is Cn. You can write Cn here, and here I write Cn by 2. Agreed? So this gives you 2 square Tn by 4 plus Cn plus Cn, which gives me 2 square 2 times Tn by 8 plus Cn by 4. plus Cn plus Cn, right? So this gives me 2 cube Tn by 8 plus 3 times Cn. Now if n equals to 2 to the power k and T1 is 0, okay, because one element, nothing to be sorted, okay, and T2 is 1, because only one comparison you require. T2 is 1. In that case, Tn becomes 2 to the power k T 1 plus k times Cn. This is 0. So you get C in log n time, which is ordered in log n. Okay? So this is matches. This matches with the lower bound of sorting algorithms. This takes order n log n time complexity to sort n elements using merge sort technique. Now another example for divide and conquer is Quicksort. So you observe that in the case of merge sort, what we did, we divided in the sequence into 2 equal parts, and recursively we call merge sort of the first part and the merge sort of the second part algorithm. Then you merges. Now in the case of Quicksort, it is little different. Suppose you have x1, x2, xn. Now what we do, that we take the first element or any one of them randomly we can select, but for simplicity we consider the first element as the partitioning element. And what it does, this element is used to find its position with reference to xn. So if we divide or we get the exact position of x1, if this sequence is sorted, right? By some technique, we partition this sequence into the 2 parts in such a way that x1 gets its position in the sequence, so satisfying the property of sorting. Agreed? So I get the position of x1 here in such a way that all these elements here are smaller than these elements, and all these elements here are larger than these elements. Okay? That means what? We select one element, say first element, which we term as a partitioning element, and this element not only gets its position in the sorted sequence, also all the elements of its right are larger than this element, and of its left are smaller than these elements. Then you recursively call the quicksort of this part, quicksort of this part. Finally, when you have one element, you get it. Now, how to partition? Say I have a sequence partition, say partition A, M, and U. What is meant that you have AM plus 1, right? I put a pointer here and I put a pointer here. Now AM is compared with this first element. If you find that this is smaller than or equal, you retain it as it is. You move the pointer here. Now, this element is compared with this. If you find that this element is smaller than AM, you go to the next pointer, next element. If you find that this element is smaller than this element, you go to the next one. Now, if you find that this element is larger than this element, then you stop here. Now you start searching from this side. Now if you find that this element is larger than m, you go to the next one. You find that this element is larger than m, you go to the next one, and so on. Finally, you will be getting a position where this element will be, you may get a position where this element is smaller than this one. So you interchange these two. You interchange these two, and then you proceed again. Okay? So finally, you will get a position here where it has crossed over. So you interchange this element with this one, and so you will find that AM got his own position. And all these elements will be smaller than this element. All these elements will be larger than this element. Now, since if I consider the size is n, then I need n plus 1 comparisons. Okay? So this is the idea of partitioning element. That is the idea of partition algorithms. Okay? Which takes n plus 1 unit of time. Now, if I have to write the algorithm, then I can write this way. Say B is equals to A M and I is equals to M. Okay? Then do I is increased by 1 until AI is greater than equals to V. Do U is decreased by 1 until AU is less than equals to V. If I is less than U, then interchange I with AU, right? After doing this, you repeat till there is a crossover. Okay? That is, I is while I greater than I less than U, less than equals to U. You do all these things. Okay? And then you have A M is equals to AU and AU equals to your V. Okay? So this is your partitioning element, partitioning algorithms. And obviously that this takes order n plus 1 unit time to do the to get the partitioning position, or to get the position of x1 in a subsequence of n element. Now, if I have to write the quicksort algorithms, so you have quicksort A, P, Q, that is, we are looking for to sort a P to a Q. Here, one thing you remember, I forgot to mention that instead of U, it is U minus 1. Instead of U, it is U minus 1. That is, we are partitioning the sequence from AM to AU minus 1. Okay? If P is less than Q, then J is equals to Q plus 1, and then I call partition A, P, and J Then we call quicksort A, P, J minus 1, because that means the position, first position, that is pth position, got its own position, which is J, and then you get quicksort A, J plus 1 Q. So idea is very simple, that what happens that I have, this is P and this is Q. So I get a J, this AP moves here, all these elements are smaller than AP, all these elements are larger than, so recursively I call the quicksort of this part, recursively I call quicksort of this part, and as long as P is less than Q, we do these operations. Now, this quicksort algorithm is worst. Can you tell me when? You observe that this complexity is dependent on that partition technique. So we are assuming that the J is here, but it may so happen that all the elements of this part are larger than this. Then this quicksort will not have any meaning because there does not exist any elements to this side. Okay, and you have remaining n minus 1 elements to be sorted by this. So again, next iteration you may have that all these elements are larger than this element and so on. So in that case, what happens? If Tn is the time complexity, then you need order n times to partition, and size is not reduced. Only one element is one side, and the other side there is nothing, no elements, right? This side, no element. This side you have n minus 1 elements. So you have Cn plus Tn minus 1 plus T0. T0 is 0. So you get next time Tn minus 2 plus Cn minus 1 plus Cn. Right? Next time, again, no elements in one side, so you get so you have n minus 1 C 2 C 3 Cn. This is 1, and 1 means T1 is 0, so you get C 2 plus 3 plus n, which is order n square. Okay? So in the worst case, it comes order n square. Now in reality, what it means, that when the elements are in increasing order or decreasing order, you will find that partition routine will give you, will not give you the good partition. It will find that one side you have n minus 1 element, the other side you will not have any element. So the complexity in the worst case becomes order n square. Now what is the best case? Can you tell me? The best possible case is when the partition elements divides this whole sequence into two equal parts. In that case, the time complexity becomes Cn into 2 times Tn by 2. If it is Cn plus 2 Tn by 2. So I can write Cn plus 2 times Cn by 2 plus 2 times Tn by 4, and this becomes Cn plus Cn plus 2 square Tn by 4, right? And you can show this is nothing but Cn log n, which is order n log n. So in the best case, it is order n log n. In the worst case, it is order n squared. Now let us try to find out the average time complexity or average number of comparisons you need in the quicksort. Let us assume that TAN is the average time complexity. This is nothing but Cn is the time for the partitioning plus 1 by n actually, to be in exact, it is n plus 1, and it is 1 plus n summation, say T A K, it should be k minus 1, T A n minus k. This is k minus 1. K is 1 to n. Okay. What it means? That you are partitioning it. This is k. So if it is k, you have n elements. So this side it is n minus k. This side you have k minus 1. And k can be 1. K can be 1 to n. K can be 1 to n. Okay. So that is the time complexity, average time. Why 1 by n? Then we are assuming they are equally likely. So that's why it is 1 by n. So this gives you basically n times TAN is equals to n into n plus 1 plus 1 by, no, plus T0 T1 Tn minus 1 plus Tn minus 1 T0. This is nothing but n into n plus 1 2 times summation T, this is TA1 TA1 plus TA2 TAN minus 1 TA I is 1 to n minus 1, because TA0 does not have any meaning. Not only TA0, TA2 also does not have any, TA1 also does not have any meaning. The understanding that TA0 is equal to TA1 equals to 0. So I take I equals to 2 to n minus 1. Now I want to solve this. In order to solve this, let us replace n by n minus 1. What I get? N minus 1 TA n minus 1 is equals to n minus 1 plus 2 times I equals to 2 to n minus 2 TA I. Now if I subtract this, I get NPAN minus n minus 1 PAN minus 1 here I get n square get cancelled 2n and here I get plus 2 times PAN minus 1. Okay? So if I bring this element this side, I get PAN is equals to 2n plus n plus 1 PAN minus 1. Now dividing both sides by n into n minus 1, n plus 1, that is I get PAN by n plus 1 plus 2 by n plus PAN minus 2 by n minus 1. This gives me 2 summation over 1 by k. K is equals to 3 times 3, so plus T A. So if I write here 3, if I write here 3, this becomes 1, this becomes 2, okay? So TA1 is 0. So this is equals to 2 times summation k equals to 3 to n plus 1, 1 by k. This is less than equals to 2 times integration 2 to n plus 1, 1 by k dk. And that is equals to 2 times log k and n plus 1, 2, that is 2 times log of n plus 1 minus log 2. Okay, so that is T A n is less than equals to n plus 1 into 2 times log of n plus 1 minus log 2, which is order n log n. So average time complexity to sort n elements using the quicksort technique is order n log n. See, this I could have avoided, but just for the completeness sake, I felt that I should tell you how to compute the average time complexity of an algorithm. Now, let us consider another example, which may be the last example today. And hopefully, you have been taught that algorithm, which is finding the kth element, kth smallest element of an element. This is basically due to Blum's technique, and I think I do. Have you? Oh, do you know any algorithm of such? No, right? So let us consider this algorithm and let us try to understand how it has been designed, right? See, one way is that you first find the minimum element then you find the second minimum element, then you find the third minimum element, and so on. Instead of doing that, let us think from this point of view that you have the n elements. These n elements are divided into n by 7 groups, and each group is having the 7 elements, except possibly the last group, which may have 1 or 2 or 3. Maybe may not be available because it may not be divisible by 7, and you can pad it by a large number. So you divided into n by 7 groups. And each group is having 7 elements. So this side you have n by 7 groups. Okay? And the 7 elements in each group. Now, in the constant, you use the constant amount of time, you can sort these 7 elements of each group. Right? So you sort each group in constant time. So there are n by 7, so your time complexity becomes order n by 7. Okay? Now, this is your median elements. These are all median elements of this group. Okay? Now, instead of finding the kth element, you find the median of these n by 7 medians. Okay? And recursively you can call that one, finding the median of the n by 7 medians, right, as you are finding the kth element. Now, this median, let us call it m. This is the median of median. Now, this median is used to partition this whole sequence into 3 groups. One, all the elements smaller than this. Another group is all the elements equal to this. Another one is all the elements larger than this. Okay? So basically, you will be partitioning three groups. One group, all the elements smaller than this. Another, all the elements equal to this, and all the elements bigger than this. Now, if you observe that if the number of elements smaller than this median element, if you find is more than k, then kth element is lying here. And if you find no, all the elements, this size of this number of elements, or number of elements smaller than this is smaller than k, but if I find the number of elements equal to median, number of elements such that this element is equal to k is equal to the number of elements and which are equal to the median elements plus number of elements less than equals to the median. If you find that is greater than k, then the median element is the kth element. Otherwise, kth element is lying in this zone. Okay? So you reduce the searching zone accordingly. Now, one thing I can assure you that at least 25% of the size of the n can be discarded at any instant of time or at any iterations. This is because of the fact that all these elements will be smaller than this element, and all these elements will be larger than these elements. Now, here, since this is the median, so this is, you have the half of the, that is n by 14 elements smaller than this, and this side also n by 14 larger than this. Now, this side, again, that half of this side will be larger than this, smaller than this, half of this smaller than this, half of this smaller than this. So this is giving you the 25% element smaller, at least smaller than this, and the 25% will be at least larger than this. And you cannot draw any conclusion on this part. So it can give you the assurance that at least 25% of n elements you will be discarding at any instant, at every iteration. Now, in order to find the complexity, if I have the T and K is the time complexity to find the kth element from the n elements. So first you will be doing the sorting of each group. There are n by 7 groups, so time needs order n by 7, and after that you will be calling the median elements. So basically you have n by 7 and k is n by 14, and after finding that you will be discarding 25%, so size will becomes T3 n by 4 and then k. Okay? And the solution of this is order n. I am not discussing how to solve it because it is a two-dimensional recurrence relation which I don't want to discuss in this class. Another example for the divide and conquer which you can try yourself, which is matrix multiplication. Here I will not discuss in detail. Suppose you have the two matrix and you partition it to the two parts. So this is, suppose you have A11, this is submatrix of A12, 2-1 and A22. You have B11, B12, B21 and B22. Then C11 is can be computed by computing that A11 dot B11 plus A12 into B21, right? Similarly, you can compute the C12 and C21 and C22. So this can be done recursively using the divide and conquer strategy that you can try at home. In the next class, we'll be discussing about the other strategies if possible. Tomorrow, next class, we'll be talking about greedy method and dynamic programming, and if time permits, little about the backtracking algorithms.